Please go ahead. Huh? Make your This is the sequel presentation of your work. Yeah.
Okay. So, sir, can you see the screen?
Yes. Yes.
Okay. Thank you, everyone, for being here. This is the second part of the talk that we discussed last time, and the title of the talk is estimation of bulk viscosity of dilute gases using molecular dynamics simulations. And in the previous presentation, we discussed where does the bulk viscosity appears in the Navier-Stokes equation, and what are its physical interpretations and what are its applications. And then we looked into what are the available methods for estimation of bulk viscosity in brief. So if you look at this summary of available methods, all of these methods have some sort of limitations, like sound absorption and dispersion experiments give bulk viscosity with, as a frequency dependent value. But in reality, if the bulk viscosity is a transport coefficient, it should only depend upon the state of the fluid rather than the process. And similarly, Rayleigh-Brillouin scattering cannot account for vibrational modes. And if we come to this numerical methods, all these equilibrium methods are equilibrium methods. So they do not tell us tell us about the non-equilibrium effects that may appear when the non-equilibrium is very high. And they also have their own limitations, such as Green-Kuo method might have, or sometimes it shows long time tails. And Chapman-Enskog method is a very robust and very computationally efficient method, but the expression for Chapman-Enskog expansion relations are difficult to obtain for several or the multi-component mixture of polyatomic gases. And then in the non-equilibrium simulation, we have only one method, which is cyclic compression and expansion. Again, since it calculates bulk viscosity from by looking at the energy absorbed over several repeated cycles. So it may first of all depend upon the frequency of compression and expansion, and second thing, it might or it might suffer from issues such as mm,
Hello.
hello. Hello. Am I audible?
Yeah. Now, but you are not for several seconds.
Okay, sir. Okay, I'll then restart. Okay, the cyclic compression and expansion method. First of all, it may give bulk viscosity values which are dependent upon the frequency of the sound wave. And second, since it measures bulk viscosity from by taking energy by looking at energy absorption over several cycles, so it does not give much insights on what is happening inside one single cycle. So these limitations brings us to the first motivation of the present work, which is that a new first principle method is required, which can overcome the limitations of existing method. Second thing, the Green-Kuo method, which is the most popular method in computational or numerical methods, involves several hyperparameters that affect the precision of calculated values and required computational cost. And finding optimal values of these hyperparameters need a parametric study. Such a study exists for shear viscosity, but doesn't exist for bulk viscosity so far. And the third thing, in the literature, it is mentioned that bulk viscosity of dilute monatomic gases is zero in their dilute gas limit. But the concept of dilute gas limit is kind of hypothetical. There is no perfectly dilute gas in reality. So at atmospheric conditions, every monatomic gases should have a small but at least some value of bulk viscosity. But there are no deterministic study in literature which states that okay, this is the value of bulk viscosity of dilute monatomic acids. And the fourth objective of this present work is that or motivation is that widely accepted bulk viscosity of the dilute gas mixtures, even the most common mixtures such as air, are not available. So the objective of this present work is fourfold. First is propose, demonstrate, and validate a novel NEMD method, non-equilibrium molecular dynamics method, that calculates bulk viscosity from first principle using this equation. Second, optimize Green-Coulomb method by finding optimal hyperparameters that can be used to calculate bulk viscosity of required precision with least computational resources. And once we obtain the bulk viscosity from both of these methods, Green-Coulomb and NEMD method, we would like to compare their results. Third thing, calculate bulk viscosity of monatomic gases at atmospheric conditions. And finally, the fourth objective is to calculate bulk viscosity of common atmospheric gases such as nitrogen and water and their mixtures. Okay, so now we move towards the first objective, which is to propose, demonstrate, and validate a non-equilibrium based method. So this method is based on this equation as we discussed earlier. And if we look at the summary of the current available method, our new method would lie somewhere here. And since this study has been performed in molecular dynamics framework, so we will have a brief overview of that as well. So molecular dynamics method, it was first proposed by Elder and Wainwright in 1957. It is a particle-based atomic scale method. And in this method, we do not consider the fluid to be a continuum media. We acknowledge that fluid is made up of atoms and molecules, and then we simulate the fluid by finding the trajectory of atoms by solving Newton's equation of motion numerically. In this method, first we determine the forces acting on each of these molecules, and then use Newton's second law of motion to calculate acceleration, and then calculate velocity and update the positions. And to calculate the force acting on these molecules, we use interaction potentials such as Lennard zones and Morse potential. And finally, for this work, all the MD simulation in this work are performed using open source software package LAMPS. And we have used Lennard zones potential with the details of the parameters, Lennard zones parameters for dilute nitrogen gas given here. And we assumed the molecule to be a rigid rotor. That means we assume the vibrational mode is frozen and do not participate in the energy exchange with translational mode. And if not mentioned, then ensemble is microcanonical ensemble, and time step used is 1 femtosecond, and initial dimension of the simulation domain is of the order of micrometer, and number of simulated molecules are 3.85 million, and boundary conditions are of reflective kind of, with same LJ potential as that of for nitrogen gas. Now, coming to the implementation of this method in the MD framework, we first created a simulation domain like this and placed molecules in that. So this left-hand side figure shows the front view, and right-hand side shows the perspective of the cubical domain that we created. Once the domain is created, we imparted velocity to the molecules from the Boltzmann distribution, and then allowed the system to equilibrate at the given temperature and pressure. And once the equilibration was completed, we expanded the system with a known value of velocity divergence. And then during the simulation, we measured mechanical and thermodynamic pressure and then related bulk viscosity to these quantities using this relation. To calculate mechanical and thermodynamic pressure, we used translational kinetic energy of the molecule to calculate mechanical pressure, and then and we know that at equilibrium, the thermodynamic pressure can be related to the temperature and density using equation of state, which is P equals to rho RT. And at equilibrium, we consider, or the translational, rotational, and all vibrational temperature are having same value. So the thermodynamic pressure can be calculated using this formulation. So the overall relations we used for calculation of mechanical and thermodynamic pressure are mentioned here. And we also ignored the contribution of pairwise interaction in the calculation of pressure. And to demonstrate this process, this method, we created this domain, and then we performed a series of different steps. So the first step was to equilibrate the system for 5 nanoseconds. And then we expanded the system with a divergence of 10 to the power 8 second inverse for 15 nanoseconds. Then again equilibrated for 15 nanoseconds. Then compression with the same magnitude of velocity divergence, and then again equilibration for 5 nanoseconds. So as soon as the expansion begins, the difference at equilibrium during the equilibration, both the thermodynamic and mechanical pressure are of the similar values. So the difference is delta P is almost 0. And when the expansion begins, as soon as the expansion begins, this delta P start rising, and after a certain duration, it achieves a pseudo steady state. And then as the expansion continues, the delta P decreases. This is because this is an adiabatic expansion. So as the expansion happens, the temperature and pressure of the system decreases, and the difference delta P, and hence bulk viscosity, depends upon the state of the fluid, and that means temperature. So which decreases with temperature. So this difference also decreases. And as soon as we cease the expansion and allow the system to equilibrate, so gradually the delta P also decreases, and finally it reaches to 0. And here we can say that system has been returned to equilibrium. Now, when we start the expansion system again, the delta P also start increasing, and after a certain duration, it achieves pseudo steady state, where it increases with the temperature, or with the expansion, or sorry, compression.
It's a compression.
Yeah, and thank you, sir. So, and then finally, when we cease the compression, the delta P starts decreasing, and system again equilibrates. If we look at the variation of translational and rotational temperature during this entire process, this figure does this job, and we have plotted these two temperatures here in this figure. So you can, as we have discussed earlier in our previous presentation, that the reason for bulk viscosity effects to appear in gases is that whatever the energy loss or gain happens because of compression or expansion, this energy exchange happens only with the translational mode, and the rotational mode does not get affected directly. So if you look at this close-up view of this corner, then you can see that the translational temperature, which is marked with dashed line, start decreasing immediately and shows a kind of a corner. But if you look at the rotational mode, its slope at t equals to 5 nanoseconds is almost 0, and the line is quite parallel to the x-axis. And as soon as the difference between these two temperatures start increasing, then because of this difference between these two temperatures, the rotational temperature responds and gradually start decreasing. And similar observation can be made here, where the translational mode again shows kind of completely reverse its direction. That means earlier it was decreasing, and as soon as the equilibration starts, it starts decreasing, because it gains energy from this rotational mode. And similarly, the same corner can be observed here. And then when we cease the expansion here, they both start decreasing and finally reach to a common value. That means the system had again reached to equilibrium. So at this stage, when temp T was 50 nanoseconds, we plotted the difference between these two temperatures, delta T, with time. So please note that t equals to 0 of this plot corresponds to t equals to 50 nanoseconds of the previous graph. And on y-axis, we have delta t, difference between translational and rotational temperature, normalized by the initial difference. And if for the small deviation from equilibrium, this delta t by delta t naught decreases exponentially. And if we fit the obtained numerical data, which is green line, to this equation, we can get the rotational relaxation time. This is usually obtained from Landau's relaxation theory. So we did so and obtained rotational relaxation time equals to 0.53 nanosecond at 412 kelvins. And with this, we can also calculate rotational collision number, which comes to be close to 3. And if we compare it, this Z rot value with the experiments, this agrees with the experiments, because different experiments report Z rot values from 2 to 6 in this at this temperature. And if we can also calculate bulk viscosity again using this rotational relaxation time, and it was obtained as 0.9 into 10 to the power minus 5 Pascal seconds. Now we study the effect of order of process, because earlier we performed first compression and then first expansion and then compression. But what if we reverse the order of the process? That means first we perform the compression and then expansion. So we have two different cases. Now you can see. Hello. Yes, Kishore.
Sorry to disturb.
Yes, please, please.
Like you calculated the bulk viscosity value, right?
Mm-hmm.
You like in the previous slide you were showing.
Mm-hmm.
So did you also calculate the shear viscosity?
Yes, we did. Oh, but shear viscosity we didn't calculate using this NEMD process. We did just to validate our molecular model, and it agreed very well.
I mean, like, because in many of the works I saw, like they give the values of the ratio, like mu by mu b.
Yes, yes, yes.
So I just saw mu. So I wanted to know, like, if you also have the mu value.
Yes, we have.
Okay. Then maybe.
But for this part of work, like first work, we have reported our results in terms of directly bulk viscosity rather than ratio of bulk to shear viscosity.
Okay.
But when we come to Green-Kubo simulations, we have reported both shear and bulk viscosities.
Okay.
Thank you. Okay. Thank you, Kishore. So here you can see that the red curve shows the curve obtained by first expansion and then compression, as we did in previous slides, and then this blue curve shows case 2, where first compression and then expansion was performed. You can see that there is not much difference between these two curves. But by close inspection, you can see that during the compression phase, the agreement is really good, but during the expansion phase, there is a slight difference. And the reason for this difference is that when in the second case, when we started the compression, so we started from exactly the state where this case 1 ended. So the state of the fluid, that means temperature and pressure are same. But once this compression phase is completed, then because of the non-equilibrium, or sorry, the non-isentropicity that comes with the bulk viscosity and shear viscosity, and also the heat conductivity, the temperature of the system is increased. So the temperature of the system is not same as the previous one. And you know that as we discussed earlier, the delta P and bulk viscosity depends upon the temperature. So because of this difference in the temperature, there is a slight increase in observed delta P. And to support this argument, if our argument is true, then if we plot delta P against the temperature, we should not see the difference. So which can be observed here. So if here we have plotted delta P versus temperature for both of the compression, both the expansion and compression phase, and you can see that there are quite good agreement among them under within the statistical limits. Now as we have used divergence, velocity divergence, which is 10 to the power 8 second inverse. So it may appear that it is too high. Just to ensure that, and the added advantage of this method is that when this gas expands, since it is an adiabatic expansion, so both temperature and pressure changes simultaneously, and therefore from a single simulation we can get the variation of bulk viscosity with temperature, as bulk viscosity is plotted on this right hand side y-axis and delta P is plotted on left hand side y-axis. So and the bulk viscosity is a function of temperature, and therefore this quantity would be a fair approximation of bulk viscosity only if change in mu b in one relaxation time is small enough so that the effect of continuously varying state on calculated mu b can be ignored. Why? Because suppose if you look at the state, and since this as soon as the expansion begins, system reaches to a delta B corresponding to that particular temperature and pressure. But if the temperature is changing too fast, then before the system achieves the delta P corresponding to that particular temperature, system would move to another temperature. And therefore, we won't be getting a correct value of bulk viscosity from these simulations. And therefore, we need to ensure that the change in temperature and change in bulk viscosity in one single relaxation time is small. And in this simulation, we observed that delta mu b in the delta T of 0.53 nanosecond is 3 into 10 to the power minus 7 Pascal seconds, which is at least 2 order of magnitude smaller than this bulk viscosity. Therefore, the bulk viscosity obtained in this fashion are indeed correct bulk viscosity corresponding to this temperature. Okay. Now we also address the same question from a different perspective. So the first question is, why do we need this high value of bulk viscosity? The answer of this question lies in the discussion that we will follow here. The mechanical and thermodynamic pressures are calculated using average kinetic energy. And due to statistical nature of problem, mechanical and thermodynamic pressures have fluctuating components. And amplitude of fluctuations depends upon the number of simulated particles. And for statistically meaningful estimation of bulk viscosity, fluctuations should be at least an order of magnitude smaller than the signal, which is a difference between mechanical and thermodynamic pressure. And the number of simulated molecules are limited by the available computational power. And since in this simulation we have used 3.85 million molecules, fluctuations were of the order of 50 pascals. And since 1 minute, sir, my system is responding very slow.
Okay, sure.
Let me close some applications. Okay, sir. So yes, since bulk viscosity is measured with this relation, and to measure bulk viscosity accurately, we need to have the fluctuations of the difference between these two quantities at least an order of magnitude larger than the fluctuations. And that means we need, since the fluctuations are of the order of 50 pascals, we need a difference at least 10 times larger than this. And since bulk viscosity is of the order of 10 to the power minus 5, and this difference is 500 pascals, the desired difference, so bulk viscosity should be at least of the order of 10 to the power 8 second inverse. Now, higher the divergence, higher the non-equilibrium. So how do we determine whether our non-equilibrium is too high? To do that, we define a quantity psi, which is difference between translational and rotational temperature divided by equilibrium temperature, and plotted it for our simulations. And in the entire simulation, you can see that this psi remains between minus 0.1 to plus 0.1. Valentini et al. Studied the variation of rotational collision number with the variation of psi. And you can see that minus 0.2 plus 1 and plus 0.1 would lie very close to this line, and there is not much variation in Z rot with this psi. So we can say that, okay, our non-equilibrium is sufficiently low. One more interesting observation can be made from this graph, that the peak of this graph for expansion is formed at the end of the expansion, whereas for compression, the peak is formed at the beginning of the compression. Why? Because this is an adiabatic expansion and compression, and pressure and temperature are lowest at the end of the compression and at the beginning of compression. And from the kinetic theory, we get to know that pressure, product of pressure and relaxation time is constant. So since here the pressure is minimum, so the relaxation time is highest, and same is here. So since the relaxation time is more, so higher the non-equilibrium. Now, as we mentioned that in this calculation of pressure, we ignored the pairwise interactions. So is it justified? To address this concern, we plotted the variation of kinetic pressure and pairwise interaction in this graph. You can see that the kinetic pressure is of the order of 1, whereas this pairwise interaction is of the order of 10 to the power minus 4, which is 4 order of magnitude less than this kinetic pressure. So first thing is the pairwise interaction is much smaller than the kinetic pressure. So this is this can be ignored. And the second argument here is that the contribution of pairwise interaction remains almost same in mechanical and thermodynamic pressure. Why? Because in both the cases, the expansion is slow enough so that the gas fills all the simulation domain. So when this in an imaginary scenario, if we take the system to the current non-equilibrium state to equilibrium state, the density of the system won't change much. And since density is not changed, so pairwise interaction pressure is also same. Therefore, and the bulk viscosity calculated depends upon the difference between these two pressures. Therefore, the bulk the effect of pairwise interaction get cancelled out in this method. So we can safely ignore this component from our calculations. And now we look at the since we have completed a complete cycle of compression and expansion, so we look at the PV work done in a complete cycle. And this line, the lower line, which is marked with dash and dot, is from expansion, and this dash line is from compression. And you can see that there is a hysteresis formed, and there are two reasons for this formation of hysteresis. First is, of course, because of because of the non-ideal nature of gas. As the gas expands or compresses, it brings some non-isentropicity, and then these curves deviate from the curves of some ideal gas, which do not have like some inviscid gas. And the second argument here is that during the compression, mechanical pressure is higher than thermodynamic pressure, and during the expansion, mechanical pressure is less than thermodynamic pressure. So here, even if we have same total temperatures or same kinetic energy of the system, the mechanical pressure of during the compression is higher than mechanical pressure during the expansion. That means the PV work done by the system is more during the compression and then expansion. Therefore, the compression figure further rises up, and this is kind of gives us the reasoning behind why this hysteresis is formed. And now we study the variation of bulk viscosity with the temperature and pressure. And here we have this figure shows the variation of temperature with bulk viscosity. And to obtain since we wanted to keep the pressure same as 1 bar, so we have to obtain each data point from different simulation. And to do so, we started our initial condition of the simulation such that during the adiabatic expansion, the desired temperature and pressure system achieves the desired temperature and pressure simultaneously. And by doing so, we obtain the obtained result are plotted here with the plus symbols. And you can see that the obtained results are kind of in the middle of the previously reported values. Then we wanted to study the variation of pressure. But the variation of pressure would be easy to study if we keep the temperature constant. And the easiest way to do in molecular dynamics is use of thermostat. But it has been shown that thermostats sometimes interfere with the dynamics and create artificial artifacts. To verify that we do not, if we apply thermostat, we do not have any kind of computational artifacts, we perform the same study, that means variation with the temperature, using isothermal simulations, and obtained results are plotted with the plotted here by green dots. And you can see that both the green dots and red colored plus symbols matches very well. That means we can safely apply thermostats in our simulations to study the variation of the pressure. And the reason why we got the same value is because the thermostats we used is Nuse-Hoover thermostat, and that interferes only with the translational motion, not with the rotational motion. And in this curve, we have shown variation of pressure in this study. You can see that at pressures above 1 bar, the obtained bulk viscosity remains almost independent of pressure. But when we are looking at lower pressures, the bulk viscosity depends upon the pressure and decreases, in fact, decreases with pressure. And we will discuss about the reasoning behind this trend in later slides. Now we report the error associated in our simulations. To do so, we have generated 4 different trajectories of the same simulations. All these trajectories start from same macroscopic but different microscopic initial condition. And here you can see that for 90% of the times, fluctuations between all 4 curves lies within the plus minus or less than, variation is less than 5%. And if the black curve shows the average of all these curves, and the standard error for all these curves, the black curve is of the order of 10 to the power minus 9 Pascal seconds. One of the advantage of this this method is that over the other previously reported method is that it is a non-equilibrium based method. So it allows us to study variation of bulk viscosity with velocity divergence, which couldn't be made possible with the previously available methods. And to do so, we repeated our simulations at different value of velocity divergence for both compression and expansion. And you can see that for tilt velocity divergence 10 to the power 8, we get bulk viscosity values almost independent upon the magnitude of velocity divergence, but although they depend upon the direction of non-equilibrium, that means whether it is compression or expansion. But again, but as the velocity divergence increases beyond 10 to the power 8, the bulk viscosity increases for compression and decreases for expansion. And we will look at this why this non-equilibrium effect appears only at 10 to the power 8 in the later slides. Now we have completed our first part of the presentation, where we studied the we have calculated bulk viscosity using the NEMD method. Now we move to the second part of the presentation, where second objective, where we will use Green-Kubo method to calculate bulk viscosity. The Green-Kubo method uses Green-Kubo relations, which are derived using fluctuation dissipation theorem from linear response theory. These relations express viscosity coefficient in terms of integral of autocorrelation function of components of pressure tensor. And these and to determine bulk viscosity using these methods, one can perform an molecular dynamic simulations of fluid in equilibrium conditions, and then calculate pressure tensor using the information of velocity of particles and intermolecular forces. And then finally, the pressure tensor or the components of pressure tensor can be used to calculate autocorrelation function, and hence integral of autocorrelation function, and then finally viscosity coefficients. And these relations, Green-Kubo relations, as you can see here by the angle brackets, requires ensemble average. The average can be performed in two ways. First is time average. That means time average over several different time origins. Since we use equilibrium simulation, so any randomly chosen time instant can be chosen as t equals to 0 to calculate ACF or autocorrelation function, and then we can proceed with that. And the second method is to perform averaging, is that we generate different trajectories starting from the same macroscopic but different microscopic conditions, and then perform average over that. Practically, for the optimum use of computational resources, a combination of both of them is used. And in this approach, by using the combination of these two ways of statistical averaging, we can obtain desired precision with the least computational efforts. And to do so, we need a parametric study by varying these two parameters, and such studies are available for shear viscosity, but has not been reported so far bulk viscosity. So we performed. So what we did is we performed generated 240 different simulation trajectories, each of which was a length 900 nanoseconds, and then calculated autocorrelation function and its integral for each trajectory at the interval of 100 nanoseconds. And then we took average over various number of trajectories like 10, 20, 30, 60, 120, like this, and plotted the integral of autocorrelation function IACF in this animation. As you can see that as the length of the simulation increases, all the simulation converges to the same, tends to converge to the same curve. And here we took the most accurate curve, which was average of 240 trajectories, each of which was of 900 nanosecond length, as a base curve, and calculated difference between other curves, and regarded it as a residual or error, and plotted the residual here. And this animation shows variation of these errors by changing the length of simulations. And by this study, we observed and concluded that increasing trajectory length alone is not inefficient. And if we perform average over several different independent trajectories, we can speed up the convergence. And for error less than 2%, and for shear viscosity, we recommend calculating average of 120 different trajectories, each of which is length of 100 nanosecond. So all these results were for shear viscosity. Now we performed a similar analysis for bulk viscosity as well. And these animations are same as before. And based on this study, we recommend that for error less than 2%, we should use 120 different trajectory, each of which is 200 nanosecond length. So we can see that the average statistical sample size required to achieve similar value of precision, the bulk viscosity requires a more larger sample size than the shear viscosity. And we have also did strong scaling analysis to study the efficiency of parallelization in these simulations, and this table shows the results. And as it can be observed here, that as the number of processor increases, that the efficiency of the simulation decreases. So the reason behind this poor strong scaling is that in Green-Kubo method, the MD simulations are typically done with a few hundreds of molecules, which is quite small for efficient parallelization. And if we increase the number of processors, the system or the computer spends most of its time in inter-process or internodal communication, rather than actually calculating forces for the MD progress of MD steps. Therefore, if we have availability of several different multiprocessor machine, then it is using more number of trajectories, with each of which is of shorter length, is more efficient and yield convergence in smaller time. And since we have used, it is an equilibrium based method, so and we use periodic boundary conditions in this method, so any number of molecules in the simulation domain would effectively represent the infinitely long system. But if we decrease the number of molecules to too small or too few, then we are likely to get system size effects. To study that, and we want to use the minimum number of molecules in the simulation so that we can minimize the computational cost of the simulations. And to this end, we have repeated the simulations or calculated both shear and bulk viscosity for 4 different systems. And one was having 64 molecules, another was 128 molecules, and another was 500, then and 1372 molecules. So here you can see that the shear viscosity, all the shear viscosity curves merge to one, and system size effects are even negligible for system as small as that of 64 molecules. But for bulk viscosity, there is a small deviation was observed for system with 64 molecules. Therefore, we recommend at least having 120 molecules in the system. And then we calculated shear viscosity of nitrogen using Green-Kubo method. And here these pink dots or pink circles represents calculated shear viscosity values from our simulations, and this green line shows viscosity values obtained, experimental viscosity values obtained from NIST data set, and an excellent agreement between the calculated and experimental values has been observed. Now we report bulk viscosity values using obtained using Green-Kubo method, and these yellow circles represent values obtained with our results. Sorry, in our simulations, and you can see that these values lie somewhere in the middle of the previously reported values. Since bulk viscosity can also be related to rotational relaxation using rotational relaxation number using Tiszazi relation, so we have also calculated Z rotational value, Z rot value using our bulk viscosity values, and compared with the available data from the literature. Since Z rot is very widely used in the simulation of non-equilibrium flows, so it is a very widely studied number, and we have plenty of data available in the literature for this quantity. And here the green dots represent the values obtained in our study and compared with the other results, and we can see that our results, the green dots, matches very well with the previously reported finding by Valentini et al. In 2014. And then we study the effect of pressure on bulk viscosity and the convergence of IACF, or integral of autocorrelation function. So for this, we have repeated the simulations for 3 different pressures: 0.25 bar, 0.5 bar, and 1 bar. And you can see that in contrast to the NEMD method, all the bulk viscosity values converge to one single value, and all the shear viscosity converge to one single value. But you can see that as the pressure decreases, the autocorrelation length required to achieve convergence also increases. And to get more insight on this required autocorrelation length to achieve convergence, we plotted or rescaled this x-axis by dividing the time axis by respective mean collision time. By doing so, we have rescaled the x-axis to in terms of multiples of mean collision time. And when we did that, surprisingly, all these curves merged into one. That means that irrespective of pressure, all these curves require same autocorrelation length in terms of mean collision time to achieve the convergence. Or it implies that this length of or the correlation length to achieve convergence is not just a computational quantity, it has some physical significance. And since the required autocorrelation length is lesser for shear viscosity than the bulk viscosity, we can say that, and this ACF essentially tells us how long a system takes to forget its history. We can say that if a dilute gas takes longer to forget its history of normal stresses and then the shear stresses. We also performed a similar study for variation of temperature, and results are shown here. But since both shear and bulk viscosity does depend upon the temperature, to ease our comparison of the different curves, we normalized all of these curves with the respective shear and bulk viscosity values. By doing so, we obtained this figure, and you can see that the shear viscosity marked with dashed line do not show any kind of dependence on the temperature. Whereas for bulk viscosity, as the temperature increases, system takes more longer time to achieve the convergence. Then finally, we compare the bulk viscosity values obtained from EMD and equilibrium and non-equilibrium methods. And to do so, we want to have minimum value of non-equilibrium, because since EMD Green Kubo is an equilibrium based method, and so we want to have a least non-equilibrium in our NEMD method when we compare results of both of these methods. And to do so, we would definitely like to use the divergence of velocity as low as possible. But this is the minimum we can go is constrained by available computational resources. Although in the previous study, we have calculated, we have had one data point at 2 into 10 to the power 7, but because of the higher uncertainty in these data points, we have repeated the simulations. And to increase the precision of newly obtained results, we performed we generated 7 different trajectories of the same simulation and then taken average over them. And the obtained results are marked with this green symbol, circles, and the squares in blue color. And it can be observed that that the Green Kubo method results of Green Kubo method marked with dashed line are closer to the bulk viscosity obtained from compression than the expansion. And if we compare the characteristics of these two methods, Green Kubo method sometimes may face long time tails issue, which we do not have any kind of such issue with this NEMD method. But this Green Kubo method is computationally cheaper, but this NEMD method is 3 to 5 times more expensive than Green Kubo method. And since Green Kubo method is an equilibrium molecular dynamics based method, so it does not account for non-equilibrium effects, whereas this continuous expansion and compression method takes into account of non-equilibrium effects. Finally, before moving to the third objective of this present work, we finally address the reasoning why in NEMD method bulk viscosity shows variation with velocity divergence and pressure. So bulk viscosity can be regarded as transport coefficient, which does not depend upon the process, but only depend upon the state of the fluid, only if the deviation from the equilibrium is not too high. That means system should be its system should be close to equilibrium. This near equilibrium condition translates to in mathematical form by this expression where the flow characteristic time should be smaller than the relaxation time. And we can see that the rotational relaxation time at 300 Kelvin, we obtained it to 0.63 nanosecond at 1 bar. And to get a rough estimate of flow characteristic time, we can use inverse of velocity divergence, because velocity divergence has a unit of second inverse. So its inverse would give a quantity in time units. So for a divergence of 10 to the power 8 second inverse, we get flow characteristic time as 10 nanoseconds, whereas for divergence of 10 to the power 9 second inverse, we get flow characteristic time as 1 nanosecond. Now if we compare these flow characteristic time with the rotational relaxation time 0.63, you can see that this 10 nanosecond is significantly or at least an order of magnitude larger than this rotational relaxation time. But this 1 nanosecond is of the of the same order of magnitude as this rotational collision time, and therefore this condition is satisfied for 10 to the power 8 second inverse, but violated for 10 to the power 9 second inverse. Therefore we see non-equilibrium effects appearing at this high divergence, but we do not see any kind of non-equilibrium effects here at 10 to the power 8 second inverse. Similarly, for a variation with the pressure, which we observed only at the low values of pressure, relaxation time scales with the pressure. That means the product of pressure and relaxation time is constant. So if for 10 to the power 8 second inverse, the relaxation time was 0.3 nanosecond, but at 0.1 bar, it would be 10 times than this number. That means 6.3 nanosecond. Now, if we compare 6.3 nanosecond to 10 nanosecond, they both are of same order of magnitude. That means at lower pressure, even the non-equilibrium effects would appear at divergence of 10 to the power 8 second inverse, and for which we didn't show any non-equilibrium effects at higher pressures. So this is the reason behind why we observe decreasing bulk viscosity at lower pressures. And you can we also saw that during the expansion, the bulk viscosity decreases at higher divergence, and the same is observed at here at low pressures. Then we move towards the third objective, which is estimation of bulk viscosity of monatomic gases. To do so, we used the dilute organ gas as a model gas, and to simulate dilute organ gas, we looked for the available algebra models in the literature, and we found that there are at least 4 different models available. And to do a comparative study like which one represents the dilute organ gas better, we calculated shear viscosity for all these 4 models, and found that the potential marked with green color diamond shows closest agreement with the NIST, the shear viscosity obtained from NIST dataset. And we then continued with the same potential. And then on the right hand side figure, we show the bulk viscosity value obtained using Green-Kubo method for dilute organ gas. You can see that these markers shows the values obtained from the Green-Kubo simulations, and these lines shows the curves obtained by fitting the quadratic equation to these markers or these data points. And while fitting this quadratic equation to this curve, we have used only 3 of these points, and the excellent agreement of this 4th point on the excellent agreement of this 4th point with the predicted line shows that the variation is indeed of the quadratic nature. And previous studies has also reported that at the intrinsic bulk viscosity is of quadratic nature and depends upon the square of the density. Here in the inset, we show the uncertainty or standard error in the prediction of these bulk viscosity. We can see that for most of the points, the standard error is close to 0.6%, and for one point, it is close to 1%. Now,
Another, these results are from the Green-Kubo method?
Yes, from Green-Kubo method.
Okay, so earlier you were saying that for the monatomic gases, the bulk viscosity would be 0.
Yes, yes,
What changed?
yes. What changed is earlier when we were doing these simulations, so we were just looking at the value which were not the ensemble average that we were using was not very large.
Okay.
So
And
we didn't get any meaningful results.
okay,
So
you were mentioning one more thing about these results being in line with something.
yes, yes, yes.
So what other works, like do you be comparing your results with that other works?
No, because although previous studies have happened in 1970s on bulk viscosity of monatomic gases, and but they were like quite crude in the nature, and so their prediction was only like that the bulk viscosity of dilute monoatomic gas should depend upon the density of the pressure, density of the gas.
Like what do you think causes the bulk viscosity in the monatomic gases? Like what?
Okay, so if you remember, like in the previous presentation, we gave two different mechanisms for bulk viscosity. First is apparent bulk viscosity, that comes because of the finite rate of relaxation between translational and rotational mode. Or let me just go back to the slide number.
No, it's okay. It's okay. Continue. I mean,
No, we can go, I think.
no, it will be like it's okay. You continue, dude. I remember that.
Yeah, this one. But there is another mechanism of bulk viscosity that appears only in the dense gases or dense fluids. That is that when we expand this gas from like this gas, then instantaneously it won't expand or fill the complete volume. It will take some time to fill the complete volume.
Dense gases is a completely different phenomena altogether than the dilute gases, right?
No, every gas is dense, but the nature or extent of the dense is different.
No, I mean a lot of other things will also change, like because the theory for the kinetic theory which we use is more applicable for a dilute gas. If you are applying the same theory for dense gas, then your molecular interactions will also need to be considered.
Yes, when we are doing the Green-Kubo simulations, we have taken care of the pairwise interaction.
Okay. Mhm. So,
So
like the results which you are showing for the bulk viscosity are for the dense gas or for the dilute gas?
for dilute gas at 1 atmosphere,
Oh,
that's the like we it was not like pre-planned, but when I will show you that I will discuss later that I was calculating bulk viscosity of mixture of nitrogen with the noble gases, and in that study somehow we accidentally met with these results.
mhm. Okay. Yeah.
So because as the density changes, the intermolecular distance also changes. So the potential energy converts into the translational energy converts into potential energy. So the relaxation happens between translational and potential energy, and finite rate of which gives rise to bulk viscosity effects. And in the dilute monatomic gases, we might not have internal degrees of freedom, but we do have potential energy.
Yeah, we do have potential energy. Okay. I mean,
So this kind of relaxation can happen in dilute gases.
yeah, no, I mean, these are whatever you're saying are true for dense gases. I mean, I agree completely.
Hmm.
But when you say the same thing for dilute gases, it is slightly difficult because the theory, if you look at the
No,
theory
if you
wise,
look at the LJ potential, it never goes to zero.
no, I'm not talking from the MD perspective. I'm talking from the theory perspective. MD is fine. Like, yeah, of course, yeah, from the MD perspective, you will definitely have things here.
Mm-hmm.
But from dilute, if you look at the dilute gas theory and like when we apply kinetic theory, when you calculate the stresses or the pressure, so we take only the kinetic part, saying that the potential part is not needed. I mean, that
Yes,
is
yes,
valid. That is valid only in the dilute gas framework.
yes, yes, yes,
I cannot use that same thing in the liquids because
yes. You
there
cannot use.
Because more than the kinetic part, the potential part is very strong.
Yes, yes, yes.
So now the entire theory will also change accordingly. I mean,
Yes, yes.
a lot of other factors will also come into the picture. So that
Yes,
is
yes.
why. So I mean, I thought like we are restraining ourselves to the only the kinetic theory. So in kinetic theory, for dilute gases also, if you are able to find something like this, I mean that's a
No,
very
no.
interesting result.
No, like Kishore, we use the lamps, and in lamps takes into account both when lamps calculate pressure, it assumes it can calculate pressure for both dense and dilute gases. It does not differentiate between these two kind of
Yeah,
fluids.
yes. I mean, like in lamps, when we calculate the pressure, we will say that okay, whether we want only the kinetic part or whether we want both kinetic and the potential part,
Yeah,
or
yeah.
only the like we can have the distinction. Like we
Hmm.
restrict to kinetic part because we know the theory is dilute gas, and we will say that okay, only the kinetic part you calculate. Like the
Hmm.
stresses are coming from the kinetic part, we will restrict it. But if
Hmm.
you add the things, yeah, it will calculate it.
Yes, yes.
Yeah. So
And when I was mentioning that literature mentioned that the bulk viscosity of dilute monatomic gases depends only upon the square of the density, they have also used dense gas theory.
yeah, I mean, like that's what I'm saying. So dense gas theory is a different concept, but anyways,
So
like proceed.
I
Let us.
think Kishore, what you are referring to is a difference between physics and the theory, and that is what you are seeing. This difference is very very small. It is bulk viscosity for a monoatomic gas is, as Bhanudev was showing, it is 10 to the power minus 10. So it is
Yeah.
5 order of magnitude smaller. That actually physically it represents the difference between the physics and the theory.
Okay. No, but calculating that from the MD is something
Yeah, but
interesting.
because in MD, I think you are not making as such, I mean, beyond the intrinsic approximations that go into it. But otherwise, you are accounting for both, right? I mean, the streaming component as well as interaction component of the pressure.
Yes. Yeah.
While in kinetic theory, you would ignore the interaction part.
Yes, sir. Yes, sir. I agree.
So this difference only is getting reflected actually through this very small number.
Mm-hmm. Okay.
Okay, so hello, hello.
Hello. Yeah, we can hear you, Bhanudev.
Okay, so should I continue?
Yeah, continue. Sorry. Thank you.
Okay, since here the dilute organ gas was represented using LJ potential, so we can also present our results in terms of non-dimensional LJ units. This would enable us to calculate bulk viscosity of other monatomic gases such as neon, krypton without performing any additional simulations. To do that, we reduced our results in terms of reduced quantities. And a very interesting observation that we have made here was the bulk viscosity becomes independent of the temperature. So all these 4 points converge to the same line, same quadratic line. Yes, and then we calculated shear and bulk viscosity of LJ fluids at higher densities as well. So you can see that for higher densities, both the shear viscosity and bulk viscosity shows an excellent agreement with the previously reported values by Jagger et al. Now we move to the next part of the next objective of the present work, which is to calculate bulk viscosity of gas mixtures. And the objectives are given here. To study the objective is to study the effects of atomic mass on bulk viscosity of diatomic gas. Then mixture, then the study, if calculate bulk viscosity of mixture of diatomic gas with noble gases, then calculate bulk viscosity of mixture of nitrogen and oxygen, and hence which will represent kind of in a way air. And then finally study the effect of humidity on bulk viscosity. To study the bulk viscosity of mixtures, we represented the interaction between like atoms using LJ potential, and for the unlike atoms we used Lorentz-Berthelot mixing rule, which is mentioned here. So sigma was calculated as arithmetic mean, and epsilon was calculated as geometric mean of epsilon 11 and epsilon 22. So to study the effect of mass of atomic mass on the bulk viscosity of dilute nitrogen gas, we considered 4 different cases. So all these four different cases, the M1 and M2 of used are given in this table. So for the first 3 cases, M1 and M2 remain same, which is 13, 14, and 15. And for the 4th case, we have used different values of M1 and M2, which is 13 and 14. And in the 3rd column, we have shown the moment of inertia of these molecules. You can see that in the left hand side, where we have calculated shear viscosity, you can see that the shear viscosity increases as the atomic mass increases, and the shear viscosity of the gas with different M1 and M2 lies between the shear viscosity of the one with 13 and 14 atomic mass units. But in bulk viscosity, an interesting observation has been made that for the isotopes which have the same M1 and M2, the bulk viscosity increases with the atomic mass, but the one with the different M1 and M2 found to have the lowest bulk viscosity for among all these 4 cases. And the possible reason for the increase in bulk viscosity for the first 3 gases with increasing atomic mass is that as we increase the atomic mass, the moment of inertia of the molecule increases, and the rotational collision number is related to how easily a molecule can rotate. So as the moment of inertia increases, the bulk viscosity also increases. But for the 4th case, where M1 and M2 are different, has its moment of inertia somewhere between these 2 cases, but its bulk viscosity was found to be the lowest among all these 4 cases. The possible reasoning behind this trend might be that when we have different M1, M2, the center of mass shifts, so which might affect the how easily a molecule can rotate. Next, we studied the mixture of N2 with noble gases, and here we have considered 3 different gases: neon, argon, and krypton, and their mixture with the dilute nitrogen gas. So we can see that when we have a very dilute mix, very small quantity of dilute noble gas in the mixture, then it doesn't show any kind of much effect on the bulk viscosity of overall mixture. So for 5%, we didn't see any kind of difference between 100% nitrogen and 95% nitrogen for all the 3 cases. But if we mix even 5% of nitrogen in the 95% of otherwise in noble gas, we see a significant rise in the bulk viscosity, which can be measured. And when we were doing these experiments, for one experiment, I actually wanted to verify that, okay, does this bulk viscosity of the pure organ gas is actually 0 or not? And from that we got to the very exciting results of the previous study of dilute monatomic gas. And now we study, our objective is to study the mixture of nitrogen and oxygen, and so that we can simulate dry air. And to do that, we need a molecular model for oxygen as well. And in the literature, there have been reported several different atomic models for oxygen. And to decide which one to choose for our mixture of nitrogen and oxygen, we calculated bulk viscosity for 7 of such potentials, shear and bulk viscosity for 7 of such potentials, and observed that none of them gives both shear and bulk viscosity matching with experiment simultaneously. In that case, we decided to continue with Jevanian potential, which gives excellent agreement with the for the bulk viscosity with the results of Lordy and Metz, and also estimates shear viscosity reasonably well with the matching with the niche data set. And then we finally simulate a mixture of nitrogen and oxygen gas, and the results are shown here. We have considered 3 different compositions, and the final composition, which is 78% nitrogen and 22% oxygen, should represent dry air. And the reported bulk viscosities are shown here. Finally, we aim to simulate human nitrogen. Previous studies have reported that presence of even a small amount of water vapors lower the bulk viscosity of gases significantly. And the reasoning behind this phenomenon is given that the water vapor or water molecules have activated vibrational modes even at room temperature. Therefore, obviously, simple rigid rigid molecular models are not enough to produce effects of humidity. Moreover, most of the mixing rules cannot be applied to most of the existing water models like TIP 3P, TIP 4P, SPCE. Why? Because these water models represent oxygen with one LJ potential site and one Coulombic charge site, and the hydrogen is modeled with pure Coulombic interactions. So we do not have any kind of like mixing rules for LJ potentials for nitrogen and the Coulombic interaction for hydrogen. For luckily there have been so we need an accurate models for both nitrogen and water and their interatomic interactions. Like fortunately, there have been one study by Hellman et al. In 2019, which used ab initio calculations to develop a model for interaction of nitrogen and water. So what they did is they generated several different configuration of water and nitrogen molecule, and then performed solved Schrodinger wave equation and to calculate potential energy of these systems. And when all these simulations completed, they fitted their results in a site potential, and they represented their water model with 9 sites and nitrogen model with 5 sites. And the interaction between each site is given as with this equation, and the total interaction between these 2 molecules were given as the summation of all these interaction of all these 45 interactions, 9 from this and 5 from this. But since, as you can see, that the this equation itself is quite complex as compared to Lennard-Jones potential, and the number of interactions per interaction is also high. So we have 45 interactions per interaction of nitrogen and water molecule. Therefore, this combination is computationally very challenging and expensive. So we wanted to reduce the computational cost of the interaction model, and to this we have aimed for reducing this model into a 3-site on water and 3-site on nitrogen and kind of model. And with this objective in mind, we applied several machine learning algorithms, and we have also improved the applied CPU and GPU based parallelization manual Jacobian calculations to speed up this optimization process. But at the end, although we were able to develop a framework for this kind of optimization and to solve this kind of problems, but the final results were not good enough to final model developed was not good enough to actually use in a molecular dynamic simulations. So we decided to go with a heuristic nitrogen and water model, where in this heuristic. Hello?
Excuse me. I had a question from the last slide.
Yes, please.
What is the justification for choosing 9 sites for that oxygen molecule in the water?
There is no physical justification for that. It is just that choosing these number of sites we were able to, or the author Hellman was able to fit the data accurately.
Oh, okay. Thank you.
Because as we increase the number of sites in the system, we incorporate additional degrees of freedom.
Yeah. Okay.
It's just like if we cannot fit a curve with a quadratic equation, then we might be able to fit with like cubic equation.
Higher degree polynomials.
Yeah, it's like that.
Okay.
So we since the previous strategy didn't work, so we went with a heuristic water model. In this, we represented hydrogen and water of H2O molecule and replaced them with the interaction of pure hydrogen and oxygen gas. And then we obtained the NH and NO interaction parameters using Lorentz-Berthelot mixing rules. Then when we used two different formats of this heuristic water model. In first model, we assumed the molecule to be rigid, and in the second, we assumed the bond and the angle to be flexible. So these are the results of the simulations, and here we can see that although the rigid model results of rigid model shows convergence, but the flexible one failed to converge, and even the one rigid model which was converged, when we look at the obtained bulk viscosity for 95% nitrogen and 5% water model, 5% water, we see that the bulk viscosity of mixture is higher than the pure nitrogen, which is in contradiction with the experiments. The experiments had suggested that the bulk viscosity of mixture should be lower than the bulk viscosity of pure nitrogen. And of course, this is not surprising because the reason for reduction in bulk viscosity of overall mixture is that the water have activated vibrational modes, and in this we have considered a rigid water model, so it does not decrease bulk viscosity. And so to accurately predict or simulate the reduction of bulk viscosity due to humidity, we need to have molecular models that should be accurate. That means interaction between two unlike atoms should be represented accurately, and these models should also model the vibrational mode accurately in a quantized fashion, which is to the best of our knowledge, we do not have such kind of models are not available in molecular dynamics so far, which can which models the vibrational mode in the quantized fashion, because the current available potentials are like represents the spring, the bond and angle like a spring, and which are we have continuous energy levels. Finally, this is the last slide of the presentation, where we calculated bulk viscosity of carbon dioxide and the methane. Since they also have bulk viscosity due to higher bulk they have been reported to have higher bulk viscosity. Carbon dioxide have been reported to have bulk viscosity of the order of a couple of thousands, and the methane has been reported to have bulk viscosity of the order of some hundreds, like 400 or 500, 300. And this is because they have activated vibrational modes even at room temperature. So we cannot use molecular dynamic simulation to predict their viscosities. So in that case, we used the available published data on sound absorption to calculate bulk viscosity of these gases. And here we see that we have plotted the F by P, the ratio of frequency to pressure, and then ratio of bulk to shear viscosity ratio. And we see that the obtained bulk to shear viscosity ratio is does depend upon the frequency in both the cases, and this is one of the shortcoming of sound absorption experiment, and that's why we need molecular dynamic simulations. But we observed that these gases indeed have several order of magnitudes higher bulk viscosity than shear viscosity. Finally, we present the summary of the work. So the summary is we proposed NEMD method based continuous expansion and compression method, and this method can be used to estimate bulk viscosity of dilute gases and understand the fluid physics. The Green-Kubo method, though does not reveal much fluid physics as compared to NEMD, is computationally cheaper than NEMD method, and bulk viscosity obtained through compression is approximately similar to Green-Kubo method, but significantly greater than expansion. And at higher divergence at low pressures may cause non-equilibrium effects to appear. If this happens, bulk viscosity does depend upon the pressure and divergence. For dilute gases and their mixtures, bulk viscosity increases with temperature, which was this observation is in line with the previous reportings. And monatomic gases at atmospheric conditions have small but non-zero bulk viscosity. And the observed viscosity of bulk viscosity of monoatomic gas was of the order of 10 to the power minus 10. And in comparison to dilute nitrogen gas, for which have the bulk viscosity of the order of 10 to the power minus 5, this is significantly low. And finally, to study the effect of humidity, simple LJ potential mixing rules are not enough, and accurate potential with accurate modeling of vibrational modes are required. Finally, future scope. The compression and expansion in sinusoidal fashion can be used to mimic the sound waves and then compare the energy absorbed with experimental data. And further studies to explain the difference between bulk viscosity obtained from compression, expansion, and Green-Kubo method can be performed. And accurate quantized modeling of vibrational mode will enable study of effects of humidity on bulk viscosity of dilute gases, and it will also validate that carbon dioxide have indeed very high large bulk to shear viscosity ratio. And further studies can be conducted to explain the wave-like pattern in the difference between thermodynamic and mechanical pressure versus time curve at the beginning of the expansion and compression. I didn't show the curve here, but yes, we have observed that. So thank you for bearing me for more than 1.5 hours. Any kind of comments, questions, and feedback are welcome.
Good evening. I'm Santosh. Thanks for the elaborate and descriptive presentation. I liked it. So, I mean, I have one question. It might sound a bit trivial, but so you have said that the bulk viscosity is a function of temperature.
Yes, yes.
So, can we write it as a function of both temperature and pressure, or is it only solely the function of temperature?
So, let me just go to, I think it was slide 50. Yeah. So if we keep the temperature constant, if we keep the pressure constant, temperature bulk viscosity increases linearly with the pressure. But if we keep the temperature constant, the bulk viscosity doesn't depend upon the pressure. And the same is case with the shear viscosity. So shear viscosity does have for dilute gases does have dependence on the temperature, but it does not depend upon the pressure.
Okay.
Did I answer?
And also in the yes, thank you. And I have another question also.
Yes, please.
So in the cyclic method you have used, so you applied a sinusoidal, compression and expansion continuously, and you observe the pressure difference. From that, you have reduced the bulk viscosity.
Yes.
So my question is, so let's say if you have done the simulation for, let's say, for 10 cycles continuously.
Mm-hmm.
So will we observe any difference in each cycle? I mean, for the bulk viscosity.
Ideally, we should not, because bulk viscosity is obtained from the difference between the thermodynamic and mechanical pressure.
Okay.
So yes, as we repeat the cycles, although this is not a sinusoidal expansion and compression, means at this point we started the expansion with this rate, and throughout the 15 nanoseconds of the expansion, this rate of expansion remained constant, and then we
Okay.
performed equilibration and then expansion. Again, the rate of compression was constant. So this was not the cyclic. This was not like sinusoidal compression. First thing. Second thing,
Okay.
if we do so, although because of the repeated compression and expansion, there would be some total energy gained by the system. But with this methodology, the obtained bulk viscosity would remain same.
Okay. Thank you.
Yes, please. Thank you.
Any more queries?
Yeah, I have a question.
Yes, please.
Yeah, can you go to that ab initio slide?
Okay, I think which was 78. Yeah.
So can you explain how we get the force potential? How we get the potential using this ab initio method?
Okay. So if you remember, like you might have studied the Schrodinger wave equation. Schrodinger wave equation, where we represent a wave function psi in function of like del electronic structure x, and think I do not remember, but it was like that.
Yes, yes.
So then in the ab initio method, they first approximate. This equation is non-solvable, like just like this Maxwell-Boltzmann or the Boltzmann equation. So they first approximate this this equation by some techniques, and then use some base functions or shape functions kind of thing so that they say that okay, our final solution would be a summation of these shape functions, and then they put in this equation, and then this equation kind of gives them the probability of a likelihood of finding an electron in the electron cloud. Once we have the electron cloud, they kind of can calculate the what would be the total interaction between these electron clouds in an average sense, and from that they calculate potential energy.
Okay, got it.
So you will get a different potential energy for each of these configurations.
Any more?
Hello, Banu.
Hello, Srujan.
Yeah, like, can you go to your last slide where you calculated bulk viscosity for carbon dioxide and methane?
Yes, okay. Yes.
So, like, are these your MD results? Like,
No. These are not MD results. So, we use the results by this paper. Okay. They performed sound absorption experiments, and they reported their results in terms of sound absorption coefficient alpha.
Okay.
So then we used this formula to calculate the bulk viscosity using sound absorption coefficient alpha. So total absorption, whatever happens, is absorption is defined as the reduction in the frequency over and above that due to we have the inverse square law. And then this absorption is depends upon the shear viscosity, heat conductivity, and bulk viscosity.
Okay.
Since we already know shear viscosity and heat conductivity from other methods, so and we also get to know alpha from these experiments, we can calculate bulk viscosity.
Okay.
But this is a kind of an indirect method, and so if you have like errors in the errors in the shear viscosity and heat conductivity, they will propagate to calculation of bulk viscosity.
Okay.
And since like at higher frequencies, this frequency becomes so high that the condition of near equilibrium does not hold good. Therefore, at these higher frequencies, even the rotational mode also start acting like frozen. Therefore, you will see that at higher frequencies, at higher frequencies, the bulk viscosity is kind of reduced to zero, because even the rotational mode does not participate in the relaxation process.
Can you go one slide back where you showed bulk viscosity for here. So here in this conclusion, you made simple hysteric model is not apt for modeling bulk viscosity, right? For human. So, are there any experimental values, or how did you conclude that?
Yes, we have experimental results, not very concrete, but yes, it has been reported that by including small amount of humidity in the water vapor, air or nitrogen gas, the overall bulk viscosity of mixture is reduced.
I think that is, it is a physical thing also, right? If you have more, like in rainy season, if you have more humidity, the sound absorption is actually less, right?
Yes.
Dispersion and
Yes,
absorption.
Yes,
so
sir. We
that
have.
way, therefore, with humidity, bulk viscosity has to come down. Actually.
Yes. Wow. I didn't think in terms of that. But yes, I have observed that, because when I go to village after the rainy seasons, the voice go to like very far distance.
Yeah. So that way also it is explainable. So definitely this trend is physically, it's unphysical.
Okay, thank you, sir. I have one question.
Yes, please.
For Banu, for gaseous mixtures, which method did you use? Green Cubo or the
Green Cubo? Green Cubo.
Okay. Okay, Banu. Thank you.
Mm-hmm.
Nice presentation.
Thank you.
Okay, I think Bhanu, probably they may take more time to digest. But anyway, you made a very good presentation.
Thank you, sir.
Good. So it helps you and us as well. Some comments and sort of it prepares you well for the upcoming milestones. Okay, good, fine. Then I think we'll meet soon. Maybe someone else might give a presentation this weekend, or I'll get back to you. Okay, yeah. Thank you. Thank you, everyone. Have a good night. Bye-bye.
Thank you, sir.
Thank you, sir.